Here we'll discuss the algebraic properties of complex numbers. Complex numbers are commutative. That means that you can exchange the order of addition or multiplication and it will still be equal to the same thing. Complex numbers are associative. That means you can change where you place parentheses without changing what the expressions evaluate to, both for multiplication and addition. And complex numbers follow the distributive law. Although these properties seem quite natural when dealing with real numbers, when we try to augment real numbers or define new kind of numbers, sometimes we lose commutative property or associative property or distributive property. So for this reason, it's important to establish these properties for complex numbers. Following this train of thought, complex numbers have additive identity, which is equal to 0. And additive identity just means that whatever you multiply by the additive identity, you still keep that number. Also, the multiplicative identity is given by 1 equal to 1, 0. So then when z times any complex number times 1 will still be equal to that same number. And also additive inverse is given as minus z equal to minus x minus y. So then z minus z is equal to 0. Multiplicative inverse is a little bit more complicated. It is given by z minus 1 equal to x over x squared plus y squared minus y over x squared plus y squared. Note that z cannot equal to 0. Otherwise, we would be dividing by 0. To derive what z minus 1 is, I will denote its real part as u and its imaginary part as v, and then I will solve for u and v. We know that 1 is equal to z times z minus 1, so we have x plus iy times u plus iv is equal to 1. And so the goal here is to solve for u and v in terms of x and y. At first it would seem like we have one equation and two unknowns. However, when dealing with complex numbers, we can use the real part and the imaginary part to turn one equation into two. First, I will need to multiply everything out and get the real and separate everything into real and imaginary parts. So we get xu plus ixv plus iyu plus I squared yv. This is equivalent to xu minus yv. Since we have here I squared, it translates to minus 1. Plus ixv plus yu. And this is all equal to 1 plus I times 0. Setting the real part on this side equal to the real part on the other side, we get 1 is equal to xu minus yv. And setting the imaginary part equal to the imaginary part of the other side of the equation, we get 0 is equal to xv plus yu. So now we have two unknowns and two equations, so we can solve for x and y. I will first use this equation to solve for v. So I get xv is equal to minus yu. So v is equal to minus yu over x. Then plugging v into the other equation, I get 1 plus xu minus yu over x. This is all equal to xu plus y squared u over x. Pulling out u, we get u multiplied by x plus y squared over x. So then dividing both sides by x plus y squared over x, we get that u is equal to 1 over x plus y squared over x. Then multiplying by x over x, which is just 1, we get x over x squared plus y squared. So we found our u. So we have u is equal to x over x squared plus y squared. Now to find v, we just plug u into this equation and we get that v is equal to minus y over x multiplied by x over x squared plus y squared. The x's cancel out and we are left with y is equal to minus y over x squared plus y squared. So now we have found the multiplicative inverse, and we can now write it down. So this example demonstrates the trick you can use when solving for equations of complex numbers, where you turn one equation into two by equating the imaginary parts of both sides of the equations and the real parts of both sides of the equations.